Hello everybody, welcome to the Empire XPU workshop. My name is Andreas Wien and I will be the presenter for today. I hope you can hear me, and I will switch off my camera later to have more bandwidth. First, I would like to go through today's agenda. Here we have the agenda for today. It will be split into sessions, which which will lead 2 hours each, and we will start with some presentation which shows the advanced EM simulation using fast FDTD algorithm. Then I will introduce radar theory and applications and some Empire features for radar and antenna simulations. Then I would like to show a little bit of the Empire XPU and give a little short introduction. Then after 2 hours, we will have a break for 1 hour, and then we continue with some hands-on practice where I show the software, how it can be operated with a small example, which is a patch antenna. We start from scratch then, and then a little bit longer, I will explain a radar antenna array, design steps, and modeling. And then we should have some time for all the questions and the discussions. Some words to the organization. At any time after the workshop, you can contact me at this email address, empiresupport@imst.de, and I will then answer your questions when you have some after the workshop. If not already done, you can download the software using the link, and then you can install the software, and what you then need is a license for operating. I have already sent a demo license which should work already for about 10 days. And including in the workshop handout zip file, maybe you have received it already, or I can send it after the workshop. The license works on any computer, so at this time you don't need a registration. But if you want to extend the license, then please send a license request to the contact, and I will send then a 30 days individual license for your computer. These hands-on are step-by-step tutorials. You can just watch today and exercise them also after the workshop. Or if you like, you can also do it during the workshop. But I would recommend just to show it, just to have a look at it and do this and then afterwards. If you like the software and you want to have the license, a regular license, you can send also a request to the contact, and we will create then a quotation for your individual or for your institution. Licenses can be yearly, perpetual, node locked, or floating. So you can also use them on a network, and then up to the number of licenses which are granted then can work with the software. I will just check the number of attendees. Okay. And now I would like to start with the first presentation. So I hope you see my screen again. I will switch off the camera so we don't have problems with the network. So this first presentation shows the simulation of electromagnetic fields using Empire XPU. My name is Andreas Wien. I'm an employee of IMST in Germany since about 25 years now, and I am responsible for Empire customer relations, support, and documentation and quality management. The Empire software has been developed completely by IMST. We have our main business is the development of antennas and circuits, and we use Empire XPU very extensively in our own company for project design, but it also is distributed worldwide. Also I think we have some customers also in India, but also in other countries all around the world. Here we see a near field on a circuit. This is some antenna application. This is a car-to-car example where we see the field outside of the car and can estimate the reception, wave propagation, and also coils which are inducing some fields also inside the human body. This is also possible. So why we use electromagnetic field solvers? Even relative simple real antennas cannot be accurately designed using classical analytical techniques. And the integration aspects of antennas cannot be considered also using analytical techniques. Integration aspects means housing or any bystanders or environment in the vicinity of the antenna, for example. So the usage of computational methods is indispensable. There are several techniques available for simulation electromagnetic fields. The most prominent ones are method of moments, finite element methods, and also the finite difference time domain method. In the next slide, I would like to show the advantages and disadvantages of these methods. We see here the different methods, method of moments, finite element method, and FDTD. And here we have, for example, the meshing elements. For method of moments, we have only surface or line elements. So these are two-dimensional objects. But in the other methods, we have to use volumes. In a finite element method, we have tetrahedrons. And in FDTD, we have always cuboid volumes. If we want to discretize the objects, with method of moments, we only have to discretize the objects, and the space between the objects does not need to be discretized. In the other methods, we need to discretize the complete space between objects. Also for boundaries, especially open boundaries, in method of moments, we don't have to care about because open boundaries are implicit. Finite element methods and FDTD, they use a finite volume simulation domain, and here we apply absorbing boundary conditions. These are artificial cells which absorb incoming waves. Then the method is based in frequency domain for method of moments and finite element, and in time domain for FDTD. That means that in time domain, we cover the whole frequency range from minimum frequency to maximum frequency, and this can be chosen arbitrarily. So we excite with a pulse, and the pulse covers the whole frequency range. This is not the case for method of moments or finite element. The solver is based on a matrix solver for method of moment and finite element method, where we have a full matrix for method of moments, a sparse matrix for finite element method. In FDTD, we don't have a matrix we have to solve. We have just some vectors of electric and magnetic fields, which we solve iterative. So from one time step to another time step, there is some kind of an update equation. So we don't have to solve a linear equation. That's also combined with the effort, which is very high for method of moments, also high for finite element method, but not for finite difference time domain. So that means that the effort only increases with the number of cells linearly. And this has an advantage that we can solve very big examples with finite difference time domain without caring much about the memory. Of course, each method has an advantage or disadvantage. For method of moment, it's always complicated to have inhomogeneous material and broadband solution. Finite element method has always a problem with large sizes and also with broadband solution. And finite difference time domain has a problem with the so-called staircasing effect because our cells are rectangular, and when we discretize a round shape, the round shape is approximated with some staircase approximation. And also for high Q structures, that means resonators, for example, which can store a lot of energy, then we need long times simulation because the energy is going down only very slowly. But for all these problems, we have some solution built inside Empire XPU. The FDTD principle works as follows. We have a finite volume with some boundaries. The volume is also called a simulation box. Inside this simulation box, we have our structure we want to investigate. Here, for example, a simple filter structure, but it can also be an antenna or any other structure. Then we have some ports, which can be at the boundary or also inside. The ports we use for excitation and termination. Excitation is then done with a pulse, which we then excite at the port, and then the pulse is propagating through the structure and out again to the terminals, to the terminal ports. The structure itself is then discretized or meshed with a certain scheme. We have some rectangular cells which can vary in the size, and all these cells are then used for their update equations. That means in each cell we have located some electric field components and some magnetic field components. And in each cell, these components are then calculated. We see we have per cell, we have 6 field components, and inside the cell, we can fill it with different materials. So it's possible to have different materials in each cell. The electric and magnetic field components are arranged in a so-called dual grid. So this is shifted by 1/2 cell in each direction. So it can be easily summed over the components to solve the Maxwell equations. If we have a look at the memory requirement, we store the components with 4 bytes for each component, so that the memory we need for the structure is 24 bytes per cell. So the overall memory needed for a simulation is the number of cells NC times 24 bytes plus an overhead, which is then not so large, and some field recordings. So if we want to have the boundary, the absorbing boundary, they need additional memory, and field recordings also need additional memory per cell and frequency. So if we want to discretize the Maxwell equations, there are 2 approaches for FDTD. One is the spatial discretization. That means to transform the curl equations here to a sum of neighboring elements. And we have a time discretization here, which is then done in an update equation. We start with some initial values, E0, H0, and then step forward in time, having a certain time step. And we do this until we reach the steady state. Usually it's then the steady state when the energy is going down to 0. For example, the update equation for one component can be written as this, so that the next components can be overwritten by the old component and some neighbors. So we only have to store 1 vector, or in total 6 vectors of components for each cell. One critical point is the time step, and this is explained later. The time step here we use for the update equations is limited by the spatial resolution. This is done in this formula. And in a special case, if we have an equidistant mesh, it can be just written like this. For air material, that means the time step we use for the update equations is equal or proportional to the minimum cell size. This is the classical stability criterion developed by Courant, which means if we have small cells, this will lead to small time steps and then a long simulation time. So one strategy is to have equidistant meshing or to avoid small cells for high efficiency calculations. The total number of time step we need is typically physical time needed to reach steady state. This could be some nanoseconds or something divided by the time step, so that the overall simulation time we need on a computer is proportional to the number of cells times the number of time steps needed over the performance. And the performance is an indicator of your computer, of the performance of your computer. So for a good workstation with multiple cores and multiple CPUs, the performance is very high. For a notebook, this is is then a lower performance. Now we see that the cell size can be critical for the time step. There are some requirements for the cell size. One is that the sampling has to be smaller than 1 over n. N is the number of samples per wavelength. So the shortest wavelength has to be resolved with at least 10 or 15 cells. And another requirement is the detail resolution, the gap size, the dielectric sheet thickness, and so on. And these are the Empire mesh settings here. Typically, we use a medium resolution, which has 15 cells per wavelength and 4 cells per detail or gap of sheet thickness. Now, what we do in the simulation is we excite and terminate at one port and excite with a Gaussian pulse. This is our standard excitation. This is a Gaussian shape pulse which contains all the frequencies we are interested in. And then we get some reflection time signals and some transmission time signals. And when the energy is going down, that means if we have results or voltages and currents which are close to zero, we can stop the simulation. Typical signal responses are shown here. If we have an inductor, the response could look like this. If we have a broadband antenna, this pulse could look like this. It's also quite short. If we have a narrowband antenna, then we have more resonances because the antenna itself can store energy and it needs some more time to get the voltages or currents to be zero. And this is also the case for some filter or resonators. Then we have a lot of ripples here in the time signal, and it takes some time to have the results close to zero to stop the simulation. Some words to port elements. Here I have just depicted a very simple structure which consists of a ground plane, a wire loop or a bond wire, and a port. And the port itself can be described as a circuit which has a current source inside, a resistor. Usually we use 50 ohm resistors for ports, and we have a measurement of the current and of the voltage. So these are in principle 4 elements which are inside of a port. Outside of the port, this can be approximated for low frequency with an inductor, and then we have the ground plane here. And this is the equivalent circuit for this structure, but only valid for low frequency. So we excite with a pulse, with a Gaussian-shaped pulse, which can be expressed like this formula, and we get the currents and voltages at the output of the port, and we get the incident voltage and the reflected voltage using these formulas where the resistor is used here in these formulas to get the incident and reflected waves. And the goal is usually to have S parameters or impedances, and this can be then obtained by a discrete Fourier transformation, DFT, of the time signals, and so we can get the S parameters. So the typical simulation flow is to set up object and materials, then subdivide the simulation domain into cells. Then the cells will be discretized for the Maxwell equations in space and time, and we excite pulse at the ports. Then the algorithm is done doing the time tracking of electric and magnetic fields. And in the end of the simulation, we make a DFT, Fourier transformation of the time signals to get the frequency response. And optionally, we can do some other post-processing. So as a result, we get time signals, we get S parameters, impedance, and powers at the ports. We can record near and far fields, and then we can do some post-processing like a specific absorption rate calculation, which are derived from the near fields. For special applications, we can also calculate temperature distribution. For near fields, we can record E and H fields, so electric and magnetic field. We can get the current density, power flow, and some derived quantities. In frequency domain, we can use volumes, planes, surfaces, paths, and probes. You see here a picture of an electromagnetic field inside a filter structure. In time domain, we can also use volumes, planes, and probes, and can look at the fields at some time steps. For the far field, we usually record the near field at the boundary. So black is the boundary. Here we record the near field to obtain the far field characteristics. So we don't have to simulate the whole domain, but only the antenna and some reactive near field here. And after the simulation, the fields are then transformed to the far field using a near field to far field transformation. And then we get the directivity and gain of the antenna and other quantities which are available in the far field. So with an innovative FTT decoding, we can make a fast parallel computation on multi-core and multi-CPU workstations in a memory-efficient way. So FTTD is very efficient for large structures, and FTTD is also very well suited for parallel computation on modern CPUs. Where our FTTD technique shows accurate simulations results in very short simulation time for complex EM design, and so we enable to simulate large and more complex antennas and RF structures compared to other tools, and we get high accuracy so that we have short prototype cycles and reduce the cost during the development. Okay, so I'll just have a look at some questions. I see there is some question as well. There's a question of recording. Yes, the presentation will be recorded, and after the session, you can also have a look at the recording inside the Teams. Yeah, so this is it will be recorded inside the Teams and can be viewed after the end. Okay, I will continue with the radar. So I have to switch on the screen again. So in this talk, I would like to explain a little bit the radar principle and how we can use EM simulations for the design of radar antennas and more. The outline of this presentation is I would like to talk about antenna design basics and especially for automotive radar antenna design, but I think it can be also applied to other radar antennas, of course. Some aspects for application and market, and then we show some antenna design examples which we have done with Empire software. So a typical array antenna design is done in the following. There are different tasks. First, there is the design of a single element, of a single antenna for automotive radar. So this is the starting point for the radar design. Then we build from one element multiple elements with for rows and columns, so we can shape the beam and have a directed beam available for the radar application. This is done usually with some lump port excitation, but in reality you would need to have a feed network, and this is also some design task which can be done in principle in parallel to the antenna design. Then, of course, we need to consider casing and radome of the antenna, and Then at last, we have to simulate and verify the complete antenna module to ensure accurate results of the complete antenna module for allow a successful production. So our aim at IMST, for example, it should fulfill the specs in the first prototype. And the last point is the antenna module integration into the application. For example, if you want to have an automotive radar, the antenna or the radar is placed usually, for example, at the bumper, and we have to include the bumper and analyze also the performance of the radar. So for a single element of a radar, we have typically one patch or a waveguide antenna, or it can be also other antennas which will be used like slots, for example, or other shapes of antennas. And with a single element, we optimize frequency, polarization, and so on. Usually these core elements can be used for transmission and also for reception, for TX and RX. In the next step, we design one column. And then also design rows of the array, and we analyze the patterns for azimuth and elevation using typically lump port feeding. Lump port feeding means there is a port under the patch, and later the feed network can be then included in another design step. With this, we can also analyze the coupling between the antennas so that we can see if the coupling is high or low, and we have to use design steps for an improvement of this coupling behavior. And also here, then we can first design a feed network for rows and columns. For example, for matching and tapering the amplitude and phase. So for phase for the direction, and the amplitude taper for getting, for example, low side lobes. This is one of the target usually. So after rows and column design, we make a complete array antenna design. Again, we analyze the patterns for azimuth and elevation. So we use here the complete TX array, complete feed network, and we can study ground plane and radome effects. So radome is just some kind of a housing of this antenna module. Then we can also design the receive antennas. Again, we make we calculate the radiation pattern, and we can also design the feed network for the RX and study again ground plane and radome effects. And finally, we simulate the whole antenna system to calculate the isolation and interaction between TX and RX. We can make a final check for the TX and RX patterns, and we can also evaluate the phase difference. So phase difference is let's say very critical part for the radar, because with the phase we can detect the direction. So for some basics for the phase difference and angle of arrival. So the angle of arrival is the phase difference between two channels, yeah, which have a spatial separation. That means we have here two receivers and we have a separation. The separation is a design parameter which goes into the phase difference. So with this formula, we can estimate the angle of arrival. And with another formula, we can get the field of view. This is just given by this formula, which has a maximum for if the spacing is half a wavelength, and this decreases with a slope with d. Yeah? So if we have different separation distances, the phase difference looks like this, or d equal half a wavelength. If the wavelengths, if the spacing is exactly at one wavelength, we have a higher slope, and if it's even larger, we have even a higher, much higher slope. And the slope decreases, the FOV, field of view, decreases with the slope. But also the angle of arrival accuracy increases with the slope, so there is a trade-off and has to be optimized for the specific application. And the angular resolution increases with the number of channels. So if we have two channels, the n value is 2. If we have more channels, the resolution is lower. And yeah. Okay. So this was in principle the antenna design, but of course you also will, it is needed to have a feed network to have a certain amplitude, shape, and phase at the different antennas. And this can be designed using some divider network. Typically, we have symmetric dividers, and also we can have some unsymmetric dividers for shaping for tapering the amplitude. So we have dividers, but we have also T-junctions, which can be designed in this way or in this way. And then we can have build the network from one element to 2 elements, then we have 4 elements, and so on. And you see that this can be quite complex for a large array, and this can be also simulated and designed with Empire. So basically we have the typical applications, the automotive applications of radars. Not only radars here, but here we have a lot of sensors, and we have optical sensors, we have radar sensors, but also have laser based sensors, or also ultrasound sensors. And for different applications, we can use different technologies to have these applications, which are depicted here. So each sensor has some advantages and disadvantages. For example, the optical imaging has a high resolution, and a large field of view, but it's limited by weather and light conditions, and also a high processing workload. So this has to have a lot of electronics inside. For ultrasonic sensors, the operation is independent on weather and light conditions, but has only a very short range. So this is the drawback. Infrared has also problems with light conditions and also a short detection range. Then there's the LiDAR technology, which is based on lasers. This is high accuracy. It can detect range and position, but also here we have problems with weather conditions, and we don't get information about velocity. And the radar is less sensitive to weather conditions, has a long detection range, good resolution, and position estimation. And in principle, vehicles are very good reflectors. So these are the advantages. Of course, it has some disadvantages. The angle measurement is quite complex. Also, the target classification, and it's and this is not for fully AD. Here we see an overview of automotive radars. So we have different application, for example, collision warning, blind spot detection, parking assistance, emergency braking, and so on. So these are all these different applications where we can use radar for automotive. Then what is a good frequency for radars? We look at the different frequencies here. Usually it started with 24 gigahertz radars in about 20 years ago. And now we are in a range where we have antenna already inside the package. And in future, we have also antenna and launcher integrated inside the package here. And this goes up to from 77 gigahertz usually bis until future 140 gigahertz. So this was a little bit of market analysis where it is used. Now we have some design examples which I can show, which we have done for Empire, with Empire. So here we see a TX-RX radar antenna for 24 gigahertz. This was in principle in the early days. We used 24 gigahertz mainly. Here we see the antenna with near field at 24 gigahertz. We have some TX and RX antennas on the front side, and the back side we have some networking for combining the antenna rows and columns. And this complete antenna was then designed and simulated. The size is about 80 millimeters times 170 millimeters. The thickness of the dielectric is 1 millimeter and included 4 metal layers. There are some resistors for the Wilkinson dividers here. 7 times 24 patches for TX and RX. In Empire, this complete module needed about 3 gigabyte, using this typical resolution of 25 micrometers, and the simulation time for this complete antenna is only 5 minutes on a dual Xeon workstation. Here we see the results. For example, the return loss, where we have done the measurements and the simulation and compare it here. We see that the frequency is very well matched, and also the curves are quite close to each other. Here we also see in simulation and measurement the near field. It is just above the antennas. And here we see a picture of our design in a measurement chamber. Also here then we get the far field patterns for this antenna. Also here we match the gain very closely between measurement and simulation, and also can get quite good the side lobes of the antenna. This is in the elevation plane, and this is in another plane. Here we have a broad beam. That means we have only low value of rows, and here we have columns which have many patches in the column row. And here we have a narrow beam in this direction, and also here we have had a very good agreement between simulation and measurement. Another antenna, here we have only a TX antenna, consists of 4x12 elements. Again, we have a feed network. This time it's microstrip with Wilkinson dividers. So we see this is the top of the antenna, this is the back side. And again, you get accurate simulation of the feedback and backside casing. The frequency range was from 20 to 28 gigahertz, about 2 GB of RAM needed, and the simulation time also about 5 minutes on a computer. Again, we have some comparisons with measurements here, which shows a very good agreement. The gain, side lobe level, and elevation was as required. This is an RX antenna for 24 gigahertz, which has then 10 antennas and 10 by 14 patch antennas. This is here also used for beam forming and a dual use of antenna rows with innovative backside feed network. This kind of antenna needed about 35 minutes. Again, some simulation and measurement results, which has again a very excellent agreement and a good uniform linear array. The last one example for 24 gigahertz is this one. We have TX and 2 RX, where we also calculate the coupling between the antennas and realistic performance prediction, because we use here the complete module for the analysis. Here we need about 10 GB of RAM and a simulation time of 1.5 hours. This is an example of a 77 gigahertz radar, but this time it's not, it's only the antenna patches. But this is then an integration into the environment, and we simulate the complete integrated radar module, including the chassis, bumper, and painting of the bumper. And we get the far field and electric field strengths at 77 gigahertz. And it's simulated within 30 minutes. Yeah? So this is only not the complete card, but it's included all the important elements. And also we have here a typical integration. And this is also shown in the afternoon session, or in the second session, where we have a 77 gigahertz antenna and include it into, and I will show also to include it into a car environment. Here we see a prototype of the 77 radar module with a complete integration. This is a radar backend with Ethernet and USB interface. This is a product we have developed at IMST, and it's called a Zentire radar. This is available from IMST and can be ordered. You see the sizes, and there is also a software to evaluate the results. This is another 77 gigahertz antenna we have designed at IMST. It consists of a combinated waveguide antenna and with some radiating slots. We see here the PCB and the metallic frame, and here we see the simulation model of the TX antenna. It's about 2.5 gigabyte memory, and the simulation time is about 3.5 minutes on this machine. Here we have some design, the simulation results like the RX curves and the input matching, as well as the coupling to the other receivers here. These are the typical results we get from the simulation. These are the TXS parameters. Again, we see the desired frequency range is well matched, and also the coupling is quite low. And also the decoupling between RX and TX antennas can be simulated and evaluated here. And the decoupling between the RX, between the receivers, it can be optimized using some chokes. Chokes are elements which are resistive and can absorb some waves in the waveguides. And we see that the coupling between the two ports can be improved by 10 dB using these chokes inside the waveguide. And we see also in the phase difference that with chokes we get a more linear curve than without using chokes. Okay, this was an overview of our radar applications and simulations, and of course we will cover some topics again in the second part when we try to design a radar antenna where we also evaluate the phase differences between the RX channels, and then include this antenna also into a car example. Good. So this was the last slide for the radar application. I'm now checking some of your questions. Okay, I don't see any more question in the moment. That means we can then continue with some features. So we have seen that the basics of Empire is the method FDTD, but there are also other software competitors available which are based on FDTD. And what is the difference between Empire and other softwares? So I would like to highlight some of the features of Empire. Especially for radar applications and integration, you can imagine that this is a quite complex and challenging task for computers, and so our main focus with Empire is the simulation speed. So we want to have fast simulations of our antennas, and yeah. So what our advantage is that Empire is very fast on CPUs. Maybe you have heard that other software, they use so-called graphic cards, GPUs, which for acceleration, but this is not necessary for Empire. We are faster than others on GPU, and we do this by smart cache usage and a full core and CPU parallelization. So that means if you have 16 or more cores in your computer, the software is running on all these cores in parallel. It is very memory efficient, even compared to other software. We have a special algorithm which reuses coefficients, so we don't have to store much. We don't have much overhead for ourselves, and we do a just-in-time compilation. That means we set up the model, we mesh the model, and then the executable is generated before the simulation starts. So the executable is then optimized for all the structure which has been modeled. That means if we have, for example, metal with 0 fields, we don't have to calculate the fields inside there. If we have cells which has equal material, then we can save some memory for and reuse them, the coefficients, and so on. So we are efficient at all scales. So we have a high performance for small and for large structures. We will see later. And one of the advantages against the graphic cards is that we can use the complete RAM which we have inside the computer. This is not possible if you use GPUs. So you can only use then the memory of the GPU, but in Empire we can use the complete RAM. Another advantage is that we can operate with all common 3D and layout formats. So we can import step format, layout format like TXF or GDS or Gerber. And we can also import some vendor projects from CST and HFSS. So with Empire enables accurate full 3D EM analysis and design of larger and more complex structures compared to competitors. So why we are so fast compared to others? So IMST invented a software acceleration technique for FDTD simulation on modern CPUs. This means we make a specific assembler code, C and assembler code, for each simulation to fit in the given CPU architecture and simulation model. I will show later that the software detects the CPU which is used, and then optimizes the code for the given architecture. That means the cache size, for example, or the number of cores, or some registers, which has floating with operations parallel. We make an individual code adaptation for the latest CPUs, so-called AVX or AVX2 and so on. And then we make an efficient caching and compression of FTTD. That means the reuse of coefficients. This is only possible if you make a just-in-time compilation. But the most important thing is that our performance speed is not limited by RAM access time. So that is a typical bottleneck to have the access time between CPU and RAM, because that is the communication speed between RAM and CPU is quite slow. Yeah, and so we do a very good and efficient last level cache usage and make a multiple time step inside the small caches before we return it to the RAM. That means that in principle our speed is not limited by the RAM access time, but only by the cache access time. So, and this has a very high speed between CPU and cache compared to CPU and RAM. We make a combined update for E and H fields, and so multiple time steps are possible for the field calculated in the cache memory of every core of the CPU. To give you an idea what we are talking about speed and performance, we have here a graph available where on the x-axis we have the simulation size in million cells. In this logarithmic scale. For example, we have here 100 million cells example, or we have 1000 million cells example. The number of cells is a measurement for the complexity and size of the structure. On the y-axis, we have the simulation speed, which is million cells per second. This is the performance. Maybe you remember that the simulation time depends on number of cells, number of time steps, and the performance. And this is the performance value P. And this is dependent on different CPUs. If, for example, we use a low-end computer like a Ryzen 9, for example, we can get about 10,000 million cells per second. If we use a good workstation, for example, a dual EPIC workstation, we can get up to 50,000 cells, 50,000 million cells per second, so 50 gigacells per second. These are mostly AMD computers because they are advantages against the Intel computers. Some years ago, this was not the case. I remember maybe 10 years ago, the Intel machines were much faster than the AMDs, but this has turned that the AMD machines are quite good. And we see our competitors, which are using GPU, they can only get, let's say, up to 5 million cells per second. So this is a typical curve which has been published by Excelware for this GPU NVIDIA Tesla card. So that means that Empire, which is using CPU, is much faster than others on GPU. Then some feature about our user interface. This we will see in the second session, a little bit more in detail. So we have different methods available for model setup. For example, we can import 3D CAD data like a car, a plane, ship, or something like this, which are in the format STEP or STL or some. And we can import it using the import module. Then we have typically two-dimensional data, which are layout formats like DXF and so on, and also ODB++. Yeah? So we can import it also into this structure. And then we can import some projects from CST or ANSYS and also include it into the model. On the other hand, we can also start from scratch. So we can create primitives like boxes, cylinders, and polygons. But we have also a large library of objects, and we can also use script-defined objects for people who are experienced with the Python language. Then we can do some standard operations like move, rotate, stretch, and so we will see something about this. And also Boolean operations, we can subtract, intersect, and so on. Another thing is that we can also include some body models for simulation. This is for typically for a specific absorption rate or power density evaluation for field inside human bodies. Okay, now this was geometry, how to include a geometry, but then we need to assign some materials. In Empire, materials are associated to groups. We have a priority management for objects which intersect. So just as an example, if you have a lot of via holes in a PCB, you don't need to cut out the holes outside the dielectric, but you can just overlay the metal vias, and so that they will be recognized without cutting the holes inside. We support different material types. Of course, we have conductors with advanced loss models. Also here we have a database of materials, and we can get the values of the conductors. Then also dielectrics with loss tangent models. Also here we have a database for different materials, and they can be anisotropic, permittivity, and permeability. Then we have some artificial absorbers. We can use dispersive materials like frequency-dependent Debye models. And we have some Gabriel-based models for tissues. Then we have some specialties like coated materials, surface impedance materials, and so on. This is an example of a body model. This was created from a project called Visible Human. It contains 42 tissues with a 1 millimeter resolution, Gabriel material, and the range of application is from 50 Hertz to 100 gigahertz. Yeah. So this is just an example of the material used for the body models. So you see that in every cell we can have different material. Another specialty in Empire is that we can easily map layout on 3D objects. Yeah? So for example, if we have Here we have an antenna, a handheld, and an antenna which is placed at the bottom. The bottom is curved. We can have a planar layout of the antenna, and then it will be bended on a certain object. And this also supports, for example, if there is a parameter on the length, the parameter is also contained in this mapping and can be used for optimization of the frequency, for example. And it's also possible to define user-defined objects if there is a scripting interface available, which is based on Python language. With this, we can derive very complex objects. For example, if we have a special taper function, it would be easy to use this interface to calculate the shape and give it to the input in Empire. So it's possible to wrap around some cylinders and so on. But with the scripting interface, it's also possible to create projects and control the simulation in a background processing. So you don't need, so you can run the software also without a user interface. So in principle, it's also possible to have a a scripted simulation. And it's also used for user-defined post-processing. If you need, for example, a phase unwrap or far-field averaging, bandwidth calculation, this can also be done using some Python scripts. Okay, you need to have some programming skills, but in principle, it is possible. For excitation, we have a library of ports, which consists of lump ports. Lump ports are usually used for the excitation between conductors. Yeah? So maybe if you have two conductors and want to have a field between them, you can use the lump ports. Or we have also some feed line ports, which detect the feed line impedance, for example, and calculate the pattern, which is then used for excitation. For example, microstrip, coplanar lines, strip lines, and coaxial line, for example. And we can also apply waveguides with higher order modes, also like TE and TM modes, which can be used, for example, TE01 or TE11, and so on. These higher order modes can also be used for excitation and termination. Beside these ports, we have also some sources like plane wave. This can be done for RCS calculation, for example, or field source, which can be based on simulation or measurements. We have different possibilities to start the simulation. Of course, we can always use a laptop and run the software on the laptop or on the desktop, and it also runs very fast. Yeah, but if you want to have very large projects, or if you want to have very fast simulation, you can also run it in a network. There are two modes for this, that the client PC has the simulation control, and then it can distribute some jobs to the different server PCs, and there is a very good interface for it to run the simulation on different computers. So with this job distribution, it's possible to have batch processing, job queuing, parameter sweep, or optimization. This means here in this mode, one simulation per server controlled by the client PC. Maybe I can show it in the second session how this is done here at IMST. Another mode is the multi-PC computing, where we have again the client PC and we have only one job. And the job can be run in parallel on multiple PCs. This depends a little bit on the network speed, which is here available, because during this mode, a lot of data has to be exchanged between the PCs, and for this we need a very good network. I would recommend at least 10 gigabit network. But this mode is rarely needed because it's already very efficient on a single PC. So this is only one option which is not used very much, because today PCs are very good. Another feature which Empire offers is a thermal solver. There we can use, we can simulate the temperatures. We can enable thermal design of complex structures. The temperature distribution can be displayed together with the structure. The solver includes thermal conductivities of materials, surface convection, radiation, and a large database with known parameters. We have heat sources from EM losses and heatsink. And another feature is the so-called circuit simulation. That means that we can have, let's say, some kind of a passive structure and include afterwards measurements of a transistor, and then we can have a circuit which includes then a transistor and the passive environment, and we can do a combined or a co-simulation. We can place lumped schematic elements in the 2D design mode and support RLC elements, couplers, touchstone files. So we have here optimization and tuning capabilities for the lumped elements. Okay, some applications which I go through a little bit rapidly. As I said, we have very complex structures. We support very complex structures. Here we see a front-end module for digital beamforming. We have on one side we have the electronics. On the other side we have the antennas, and there are up to 16 layers of material and metals, which are usually where we have integrated some couplers, phase shifters, and so on. And here we see the prototype. We use here the LTCC technology for this. To simulate the complete module, we need about 16 gigabyte RAM and about 2 hours simulation time. So this is a challenge for all other competitors, but with Empire, this can be very efficiently simulated. This is another Ka band antenna which consists of TX and RX modules. This is waveguide technology and a special shape radiators with 32 by 32 antennas. The frequency is 30 gigahertz. We need about 4 gigabyte of RAM for this and a simulation time of only 8 minutes. We see measurement and the simulations are in excellent agreement. Another applications are waveguide-fed elliptical lens antennas. The lens is also used for beam direction. Yeah, so we can with different with a shift, we can direct the beam to different angles, and this is working at 180 gigahertz using a waveguide horn below and then the dielectric lens. The frequency goes from 120 to 240 gigahertz and about 15 gigabyte of RAM within 1 hour simulation time. This is an example of a 60 gigahertz wireless transceiver. Again, the top side of the prototype is depicted here. And I think if we make a animation here, we see that how the near field is propagating through the structure. This is also an LTCC, that means a low temperature co-fired ceramics. And the waveguide is built from the metal, top and bottom metals, and some via conductors. And we see how it feeds the waveguides and how we see the waves are propagating to the top. Okay, then we have some other applications like a feed horn array at Ka band. Again, stimulation and measurements, very good agreement. This is an innovative active beamforming network with 3 adjacent beam form one artificial beam. Here are an example of some satellite antennas. Again, we have here the model and the near field and far field for different beam configurations. Also here we need about only 6 minutes on a good workstation to simulate this complete structure. This is one filter example. We have here the simulation model. Again, we have here 25 gigahertz, 5-pole Chebyshev type filter with couplings and coupling sections. And this is the prototype we have measured and built with LTCC. Simulation time about 30 seconds. And we see, again, this was the first shot prototyping, and the measurement and simulation are in very good agreement. This is one example which is a little bit more sophisticated. This is a complete power amplifier with all these elements on this board. This has also some inductors on it. You see the photo and the model in comparison. Bond wires and everything has been included, with the exception of the active elements. The active elements are inside the chip. So that we have, in principle, we simulate with Empire the complex, the passive surrounding. And with a circuit simulator, we can include then the active elements like amplifiers and so on. And with this co-simulation, we can get also this, the results here, the output matching simulation versus measurement. So that means we have here several ports, and we excite all the ports to get the complete S matrix of this passive structure. And then we have this S matrix as a touchstone file and include it into a circuit simulator and connect then the missing elements, which cannot be calculated with FDTD, the active elements usually, or the nonlinear elements. We can include it with a circuit simulator and do a co-simulation. Other PCB or electronics simulation are typically that we have some structure on a board, on a PCB, and we excite some of the paths, and look for the coupling to other paths. And this can also be quite complex because of the small details. And we can estimate all the couplings and reflections and transmissions of this PCB board. It's also possible to have not a Gaussian pulse excitation, but also a lightning pulse. And with this we can, for example, model the lightning strike of an aircraft. I'm not sure if if we have an animation here. Yeah, I see. So this means we have an animation. That means we have a feed here, and then the current is flowing on the outside of the plane, and we see how the current is flowing on the surface of the plane. Okay, we can also analyze antennas on the different vehicles. Here we have a shark antenna on a plane. Let's see if there's an animation on it. Oh, it's not. Okay. Typical simulation time is 20 minutes for this kind of application. Then we have different applications which include a body model. Typically, we expose antennas on a car, for example, and place a human body in the vicinity. Can be outside or inside the car. And we look for fields inside the human body and evaluate the values. And we are compliant with the IEC and IEEE standard for these values to have different exposure and model positions possible. Here, this is one example I think we have here. Sorry, I have closed the wrong window. I hope you can. Now it should be again available. What I wanted to show is the field here. Okay. So I go on. One other example is here a front-end module in a car mirror. So we have integrated here a module with an 8x8 front-end array at 30 gigahertz, and we can analyze this tool, this field, and simulation time is here about 2 hours using about 110 gigabyte of RAM. Another application is modeling MRI coils. So for medical applications, these are typically some kind of a resonator, which is a birdcage resonator here, and there is excited a certain magnetic field inside with a certain feed network, and then we can evaluate the values induced into the body model inside for the simulation. Maybe one last applications are body variable antennas. So we can also design and analyze antennas which are used for communication between humans. So they are the design includes then the vicinity of the body models for communication applications. Here we have a typical frequency up to 6 gigahertz with 20 gigabyte of RAM, needing about 3 hours of simulation time.
Okay, some conclusions. So I think we have shown that Empire is very flexible and very efficient to model large structures, but it's also fast for small structures. As we have seen in the performance chart, the curve is nearly constant for large and for small simulations, and we get a very short simulation time. Okay, that's was the presentation, and I will just look for some questions. Oh, I see that. Yeah, sorry that yes, I think this was my mistake to close a window. I just share my screen again. I hope you can see it again. One question is, can we import files from HFSS? Yes, this is one of our import possibilities, to have files which are created by HFSS or CST. They can be imported into Empire. That means all the geometry and materials, they will be assigned, but at least the ports have to be added. Yeah, so the ports we can usually not import because we have another port methods available. But the geometry and materials, they can be imported from other software. Okay. So we don't need any GPU for our for Empire. Yeah. So we just need a usual graphic card which supports OpenGL, and this is a standard. Yeah? Each Windows laptop can be used for it. We are limited to FDTD. We don't have other solvers available. Yes, a pulse consists of many frequencies. Yeah, so let's say if you have a sine signal as a sinus signal, then you have only one frequency. If you have a Gaussian pulse, then it includes zero frequency up to a certain maximum frequency. And a single pulse is really can be used for all frequencies. Yes. I'm not sure of what you mean by CKT. So maybe you can explain a little bit. Yeah, how to check energy convergence. Yes, this is done in the following. There is a monitor inside during the simulation where we evaluate the E field and the magnetic field, the electric and magnetic field in each cell. And this is summed up and evaluated to the energy. And this is then recorded over the time. I will show it in the hands-on session how this is done in Empire. Thumb of rule for cell size. Yes, let's say if you have a gap in between two conductors, then there at least should be one cell inside the gap. Yeah, it's even better to have more than one cell. So this is usually determining the smallest cell, that is the gap between two conductors, which has to be resolved. Yeah? Another rule of thumb is that if you have your maximum frequency, let's say it has, let's say we have 10 gigahertz at maximum frequency, then the wavelength is 30 millimeters, and then the cell size should be 30/15. That means that should be a cell size of 2 millimeters at a minimum. Yeah? So this is the rules of thumb we are using. Yes, the recording will be available. I'm just checking if we have another question. I hope you can see it now again. For 7 minutes, okay. Yeah, I hope, yeah. So we have 50 minutes left. I would just check, I would just show a little bit of the Empire software as an introduction before we start the break. So this is the software installation. Usually, if you don't have a license, then it will ask for a license at this point. And at this point, we can also get the license request. And when it starts, it takes a little time for starting. And this is now the frame, the main frame. And this is the project wizard. So we can start, let's say, with a new project. This is, if we want to have, if we start by scratch with an empty project, we can use this. We can enter some structure type, if it's an antenna or a waveguide or something like this, or we just use standard. Then we have two solvers, the EM solver and the thermal solver. And here we can enter a unit. By default, it's micrometers. And here you see that you can enter the end frequency and optionally a target frequency. So this is the main, let's say, target for your frequency, but it generates results from 0 to 20 gigahertz. Then you have here the option to start to open manual or application notes. Here we can select some recent objects, recent projects. Here we have a small preview of different examples you have already done. Then there is a section for examples. There are built-in examples which can be loaded. We will start later on with this, and these are different applications for antennas, for circuits and components. All these examples are already calculated and the results are available. A lot of examples for different applications. Then we have a section called templates. Here we have the possibility to start with simple structures which are, let's say, pre-designed. Yeah, you can enter some parameters like material, height, impedance, and it will automatically generate the structure which is depicted here. Of course, this is very easy, it's just a simple line. But if you look for example, antennas, we can have a simple dipole, and you can select the frequency. If you want to have a dipole at a certain frequency, you can just enter the frequency here and some options, and then the structure is generated. Yeah, later we will use this kind of template. Here we have a little bit more complex. We have a complete array available where we can enter the number of elements in each direction, and also a beam shift if we want to have it. Here we have a horn. Yeah, you can select the waveguide size and the wall thickness and the opening angles and so on. Filters, we have some filter structures built here where we can enter the frequency and we get the filter design. So these are mainly based on some design formulas. Yeah. So all these structures. And then we have a section called tutorials. This is also very interesting for beginners. If you have a certain application, you can just start with a tutorial. Actually, this is only starting a PDF, which are step-by-step tutorials, and then you can repeat the steps which are written in the tutorials. Also for very different applications. Here we have a reflector antenna, for example, and so on. Let's start with an example. I just want to load an antenna. Let's use a horn antenna as an example. This is already the result. So when we look at this at the software, now we are in the main frame. We have different tabs available. Here we have, for example, the design in 2 dimensions, and we can enter here our objects. This is very well suited if you have a layered structure like a PCB or LTCC. Then the 2D design is a very good choice to start with. Or we can have a 3D design where we can enter the structure here. For example, I just want to create some objects here. Can do it in this way, or a circle. So very easily to set up. I will just undo it. And you can use different views. Here. And we can just create some objects like a box, cylinder, polygon. Or here we have a library of objects. For example, if you want to have 3D sphere or a twist or something like this, you have here some objects. You can just pick and place parabolic dish, a ribbon helix. Then we have here some bond wires or a torus or a helix. Some extruded structures like spirals. And we have some coaxial element, microstrip elements, coplanar elements, also SMDs, and some special things like substructures or layout, or even conformal structures. So these are the 2D design and 3D design. Then we have our simulation section. We will learn later. Here we get all the information during the simulation. Then we have here a circuit designer where we can pick and place some elements like some resistors, and then include the simulation results. I will just delete it again. These are the results. For example, the far field here of this antenna, or the scattering parameters. We see here the S parameter of this horn. We are still here in this horn. What we can say here is that we have a waveguide port, and an air section and a taper section. And here we have the results of the port that waveguide is reflecting here for this frequency, or the far field pattern in 2D is looks like this. Usually you want to plot it in a polar plot, and this is then done here in the plot format to have a polar plot or in dB. These are the angle for different planes. The theta phi equals 0 and phi equals 90 degrees. And in the 3D result tab, we have typically some field monitors. So this is in principle the structure without any results. But if we want to include the results, we can first have a look at the far field and see the pattern relatively to the antenna. Or we can have a look at the near field. Here we have one plane which we have recorded at a certain frequency, and here we have another plane for a certain frequency. And if I want to, I can make a phase loop. Here we have a phase loop of the animation. This we will learn later, how to do this. And if I start this animation, we will see how the fields are traveling from the waveguide through the taper into the space. Okay, I will again check for some questions. Okay, then I would suggest that we will have a break now and continue in about 1 hour. Okay, thank you so much for attending, and see you in the second part in 1 hour. See you. So, hello again, welcome back. I would like to continue now with the second part. Here we do some hands-on practice. A small antenna from scratch and a radar antenna array modeling and design. I hope I have left then some time to answer your questions. I saw there are a lot of questions in the chat, and I will come back to them and later. Okay, let's start. You should have, or you could have obtained this material. This is on one hand a license, a default license, which runs on every computer. I will show you how to install it. And then we have here our first tutorial, which is just a small patch. You will see that is we create groups, properties, and hide in 3D design. We create objects, support, simulation parameters, and field recordings, and look at the results. Here we model a patch antenna with a target frequency of 2.45 gigahertz. We take a Rogers substrate. The patch size is about 40 by 40 millimeters. The substrate size is about 80 by 80 millimeters. Here we will use an infinite ground plane, yeah? And you will see there is some instructions here, so you can follow it now or after the workshop, and you see there's steps and explanations what to do. But I will show it now in the next steps. Okay, you see there is a license. Yes? I will now show you how to install the license. I have deactivated my own license, and after installation, you get this icon, and after double click, the Empire simulator comes up. And this is now, you see that there's no less, now that we don't have a license here. If I click continue without license, you can still open the software and look at the results. Yeah? For example, you can browse through the examples which are built in and look at the results and so on, but you cannot save anything. With here, you can request for an individual license. If you place this button, there will be some form to be filled in, and there is some information about your PC, and you can save it and then send it to the contact email address, which I have shown before. And then we will create a license and then return it to you, and you can then install it. The install button is here. We accept this, and then we can browse for the license. No? And now I browse for this license, which is available in this folder, Workshop Handout. And I just select it and then open it, and now the license is installed. Okay, now I can restart. And now the license should work. Always takes a little time to come up. Okay, you see that the small window is not there anymore. And the first step is to click on New Project. So we start with an empty project. We keep everything here, and we just click OK. And now we see the empty structure. It does not contain anything. We have used the default values and just click OK. The first thing is to save a new project. So we click on Save As, select a new folder, maybe on the desktop. On here we create a new folder called, let's say, example 1. You can choose a new name, or you can keep it just. The name is not so important here. Or we just call it patch. Okay, now we see in our folder on the desktop, we have a new folder. There is one input file. This contains all the geometries. And here we have a subfolder called patch with the same name. And here there will be some intermediate files and also the results. Maybe we can check later. I go back to the editor. And now we see different areas. We have here, on this side, we have groups and coordinate system, mesh information, field value, menus, monitors, and variables. First, everything is created in groups. Yeah, so usually different parameters, different objects with different properties are within this group then. There is a default group at the beginning. I can just, with a right click edit name, and I call it substrate. It's active because if we have other groups later, there's only one active, and on this subgroup there will be the creation of the model. At the first step, I open the group. There's some small arrows here, and it has height and a property. Yeah? We have to change both here. Height is used usually if you want to have a layered structure, and then you can assign some height. I double click and keep the 0 at the bottom and 635 microns to the top. That means our substrate will be 635 microns in height. Conductor is always used as a default when you create a new group. It is very convenient to use always a conductor as a default value. But here, of course, we have to change it. We just double click on the conductor, and then we get the property editor. And we can select different materials, dielectric, conductor, absorber, and some advanced materials. There are also some circuit property, mesh property, and so on. But we just change to dielectric. And we can enter, for example, here permittivity and loss tangent. I can also use the database and browse for Rogers. And here we use 5800 and 5880, this one. Toroid 5880. It has a permittivity of 2.2 and a loss tangent of this with this value, and just click on OK. And then you will see that the property of this group is now Rogers with this value. Now let's create an object. There are two methods I will show. There are some creation button on the top, which is create box. I just click it. And now I can enter points in this area on this grid, or I can just use the tab key to interrupt this input. And then we get a box editor. And here I can just enter the coordinates. They should be minus 40,000. This is all in microns, yes? Minus 40,000, sorry. Plus 40,000, plus 40,000. So 40 millimeters in each direction. And then I click OK. Now you see that everything is blue, so that means that the object is quite large in this zoom adjustment. So that I click the bottom zoom extends, so we get a view of all objects which are defined so far. Okay, that was the creation of the box. Now we have the substrate. Now let's create a patch on the substrate. Best thing is to create a new group. This is done with a small button plus, add group. Give it a name. Let's say patch. Maybe adjust the color, maybe red. And again, we open the new group. By the way, we can close the other group, which we have finished. You see, the new group is also active. When I create something, it will be then on the new group. Again, we will assign a height. Now, the patch should start at the substrate top. That means 635, and it has 10 microns thickness, 645. And we can now keep the default property of conductor. Now again, we create a box, but this time using the mouse input for the creation. Let's click Create Box. And now you see in the low left area the cursor coordinates. And now we move the cursor to the desired position. It should be here at minus 20,000 plus 20,000. So we make a first click at this point. And now we click on the opposite. So now we are at the opposite. You see the window down on the left. There are the coordinates. And now I make a second click. And now I can give it a height. But I don't, because the height is very small, it's hard to access it. Yeah. So using the cursor, the mouse input is not convenient. Therefore, I have used the height information in the group, and I just make a long click at the same position, and then it's automatically used from group. We see the coordinates here. If we don't have matched the values exactly, we can override it now. Yeah? So they are okay. And you see the Z coordinates are not accessible at the moment because we use it from the group. Otherwise, if we change to custom, I can override also these values. No? So, but I use from group. Okay, that's the definition of the patch. Now we have to insert a port. And again, we create a new group. Let's call it port. And we use a height. The height should go from the ground. Maybe I told about that the ground is used as a boundary. And so therefore, we don't have to enter a ground, but it will be used as a boundary condition. So the boundary condition will be from 0 to, at the point 0. So my port should go from 0 to the top of the patch, to the patch. That's the 635. Good. Now let's create a port. This is done here with this symbol, with the battery symbol, create source. And now we have a library of ports. Here we have the so-called QTEM ports. These are feedline ports. Then we have lump ports, planar, coplanar, coupled lines, coaxial, waveguides, volume, and so on. But I will use now a lump port. And the best lump port for this patch is to use a perpendicular port, where we have top and bottom, and between there will be an excitation. Again, I can use now the mouse input for creation of the port cross-section, but I would like to add it by manually. So I press the Tab key, and I get my editor for this. And now I have to define a cross-section. The cross-section should be, I will show later by minus 9,000. Oh, sorry. Minus 9,000. 1,000. Minus 7,000. Minus 1,000. Now the port has been created here under the patch. If I disable the patch, you see the cross section here, and you see the height here. Usually the location of the port is some design task. Yeah, usually the correct position here can be also be part of an optimization. But here I know the coordinates already for this example. This is sufficient now. Good, that's in principle the steps to be done here in this editor. And now I enter some simulation parameters. For this, there is a button called Simulation Setup. I click it. And here I can enter now some details on the simulation. Again, I could enter a unit. Here I'm currently using micrometers. I don't want to change it. The structure type we select an antenna. Background material and simulation mode. We have only one port, so we don't have to care about this mode. Then we have a tab called EM Setup. Here we can enter the frequency range. I would like to start from 1.25 gigahertz. And my end frequency should be 2.5 gigahertz. This is my resolution of the frequency. It should be it doesn't have to change, but I changed the target frequency because I want to save my fields and near fields and far fields at a target frequency of 2.45 gigahertz. Okay, that's the frequency range. I can also enable loss calculation, but in the moment we are calculating lossless. Then there is some settings about accuracy, like energy decay level, time step limit, or field convergence check. Just keep the default. On demand, this can be changed, of course. And also some other settings which are not important up to now. By the way, there is an advanced button which is only seeing the parts which are necessary or advanced mode. Yeah? Then we have some entries for mesh. Maybe you remember the resolution is something which is critical for accuracy. Here we have the default value of medium. That means we have 15 cells per wavelength and 4 cells per object. We keep everything. Now we have the boundary conditions. By default, everything is at absorbing. That means that waves are going through the walls. But here we want to have a ground at the lower boundary. The lower boundary is at Z min. So we change it here to be electric. On here we have also something which is called boundary distance, but you can always keep it automatic. Just click on OK, and that's the things for the simulation setup. Then, if we now start the simulation, we only get the parameter, let's say, of the input impedance and the S parameters. Up to now, we don't have recorded any. We don't have defined any monitor. Okay. So we create far field recording. There is a button like this, create field monitor. And we select the standard recording for a far field. Now, the first thing what we have to enter is the frequency of storage. Because we have selected the target frequency, it's already defined here. But we can add more frequencies if you want. Yeah. So we don't have to. We can have a list of different frequencies. In the processing setups, there are different far field calculations. 3 are enabled by default. The first one is a phi equals 0 plane, or it's the XZ plane. Yeah. It goes from -180 to +180 for the theta value. So this is always spherical coordinates. So we keep it, but in the advanced, I want to enable a mirror because we have used an electric boundary conditions, and this means we have a mirror at the boundary. And this we do for all the far field setups. The far field setup 2 is a cut, two-dimensional cut with a phi equal 90 degrees, and this is a YZ plane in spherical coordinates. And also here we have an advanced, we enable the boundary. And in the setup 3, this is a 3D sweep. So both phi and theta will be swept, and then we get the 3D pattern for the bit magnitude, phi and theta components. Again, advanced, I check the boundary. Okay, that's all up to now. And we can start a simulation. The simulation starts with this button called Start Simulation. I just click on the button. And now it asked me to start a complete simulation. Yes. Then the options about what is done, the project will be saved. It will be meshed automatically, of course, and discretized for simulation. Now let's click OK. And now you see that it's automatically switched to the simulation tab here on the top. And we see some log window which shows the progress of the simulation. At the moment, it was compiling. That means that it was creating the executable, as I told before. And now the simulation is already done. That means the time stepping is done, and then the post-processing has followed. You see in this plot here that this is the energy over the time steps. So we have started with 0, and the energy was inserted into the structure up to a maximum value. Then the energy was slowly getting down. So this is a typical curve for an antenna. It goes down to 40 dB because 40 dB is our default decrement value. And it has calculated up to about 40,000 time steps. Okay. Maybe we go back to the log file, log window. I just want to explain something. The log window says the progress of the simulation. That means we start with some simulation. You see the Empire version and build number, and some ID numbers for the simulation, some settings. Here we have also, let me check, the memory estimation. For this example, the software needs about 78 megabyte. Then there are some internal progress, and we see the time step size. It's about 0.5 picoseconds in time step, and so on. And we see some statistics about memory and efficiency. And here the simulation starts at this point. And in the first steps, it tries to optimize the speed. So there's an automatic adjustment of the best strategy for the multiple time stepping. And then the simulation finished, about 18 seconds. And then the post-processing starts. with a typical calculation of DFT and incident and reflected waves as parameters, and then there is a far field calculation going on. Okay. Now let's change to the results. This is the scattering parameter. It resonates approximately at 2.45 gigahertz. It starts at 1.25 as we entered and ends at 2.5. And this is only scattering parameters and the plot format. I can add some more curves at results. Then we get the impedance plot. Yeah, you see the impedance in ohm for the magnitude for the real part and for the imaginary part. Then let's add a new result. These are far fields in rectangular plot. Sometimes or mostly you want to have a look at the polar plot. Then you just change the plot format to this one. And you see that are the two curves in phi equals 0 and phi equal 90 degrees. And if we add more plots, then we get the time, the voltage over the time in nanoseconds. I can arrange the plots a little bit more so to have it in this style. And here I can arrange it to have it looking like this. Now let's have a look at the 3D results. And now we see this is the 3D pattern which we have calculated only for, of course, for the plane, for the half domain, yeah, because we have an electric boundary condition. But we don't have any more because we don't have recorded now a near field. Yeah. So this is what we are doing now. I go back to the 3D design. I create a new field monitor. And this time I use a field plane. That means I have an EM field using a plane. Again, I can select several frequencies for this field monitor. And plot options we can adjust later. One thing I have to determine now is in field monitors, if I select a field plane, I have to also select the plane, and this is done in this area. And I want to have the plane in the patch area, so I enter 365, and I have to resimulate because the field recording has to be defined before the simulation starts. I just recalculate because it takes only a few seconds. Okay, let's wait until they're finished. We get the same energy. And now it's post-processing. That means the near field is already there. Then I can switch to 3D results and have a look at the near field. For better visibility, I switch off the substrate, the patch, and also the port. And I have, now it looks like this. So this shows the electric field at 2.45 gigahertz. If I want to change the style, I can just open the plot options. And here I have some options to display. Here, for example, I can select also the magnetic field, different components. Then I can also normalize it to other quantities, the scaling and the range for this agenda. As the first thing, I would like to enter an amplitude. Let's call it 50,000. And let's press apply. Now it looks like this. Here I can enable some contour lines, number of lines. Let's use the black color and apply. Gives us lines of constant field strength. And if I want to, I can I want to see the real part, and I want to use some arrows for display, and then I get some arrows showing like this. So if you like, you can play around a little bit. You can oversize them, or you can have another size. Something to play with, to have a nice style for this. Okay, that's in principle what I would like to show with this example. You see that it's quite easy to have a structure like this, starting from scratch, and it's even easier to start with a template, which we'll do in the next section. Okay, I will just check for some questions. I think, no? Maybe I will go to this. I hope you can hear me, yes? Okay. I will go to the questions later. Okay. Yeah. Let's close this and we will show the next one. Or maybe I go through the questions now. Maybe there will be some more and then we don't have enough time for it. So I just scroll down to the questions. A lot of questions. Circuits. Okay. Let's go back. Can we check lumped circuit version of microstep line or circuit? Sorry, I don't understand it correctly. Maybe we have a discussion on this maybe later. Okay, I think I have answered this. This we have answered. In principle, yes, we can select coupling between any two particular pair of elements. Yes, you just need some ports. Yeah, you have your elements and you have your ports, and then you can have you see the coupling in the S parameters usually. Yeah? Can the mesh from Empire be exported? So we can export mesh. The design mesh from MTL by STL, yes. It can be STL is can be used as export format. So we have different export formats. STL is one of them, but it's also a step format, can be used for export. But the STL is the free one, so you don't need an additional license for this. CPU requirement, it's not, it can be any modern PC, like it can be an Intel Core i5, for example. I have a Core i7 on my system. But today, many people use AMD CPUs. So in principle, you can use any CPU. Yeah? So we don't have much requirement for this. Yes, we can simulate body antenna with a Voximil, the model, with the software. Yes, we can. A lumped element model. No. What you get from our as results are S parameters. Yeah? Sometimes S parameters can be converted into a lumped circuit, but this is only valid for low frequency. Yeah, and but especially for microstrip line, this is not valid because it would have there's a wave propagation, and wave propagations cannot be accurately modeled with lumped elements. A point source, no. The source we can define is a lumped port. This is the smallest element, so it's always a deep dipole type source. Yes, I will show in later that we can have a when we start with a template, we can enter a frequency range. Yeah, so if we can design already. This is an integrated design formula. I will show. We select. This can be that when your computer or your screen does not show the OK button, then it's then the resolution is not sufficient. Yeah? So I think we need at least HD HD resolution for running the software. I think if you have only 800 pixel, then it's not working. Yeah? So you need at least a HD resolution. Yes, we can import. We can import a schematic, or we can define a schematic and can do a co-simulation. Yes, this is possible. Maybe I can show an example of this. But yeah, I will show an example of this. I just open the software again. And I'll show you how to do a co-simulation. There is an example which is called antenna matching network. Example, dipole matching network. So it consists of a dipole. Maybe it's better to view in a 3D design. This is just a dipole and a port. And here we have a circuit tab where we have the results of the FDTD simulation. So this makes an FDTD simulation, and then this is the results of the FDTD simulation. And here we can add some matching network, and then we can do a co-simulation and get this curves. If we enter some variables, for example, you see that the curves is updated without a resimulation. Yeah? So it's just here varying the inductor or the capacitor, and This is a one-time simulation. This has been done before. Okay. Yes, we can save animations of the near field and far field. There are some. There is a button for recording, and we can save it as a. I think it's a graphic and GIF format. Yes, we can create our equation. I will in the next example we will see how to do it. Yeah, okay. If your simulation is interrupted, there is no possibility to save the results. So if a power cut is there, you have to resimulate. It's no chance. Okay, I think I can go on now with this with the second tutorial. Which is the radar antenna. So we start with a single patch, as we have done before, but without not starting from scratch, but we will use a template for this. And then we make a parameter sweep. Yeah. So as I told you in this radar presentation, you start with a single antenna, optimize it for a frequency and or for some patterns. And then you go on with your array, yeah. So and then we will make an array creation after we have optimized the patch, and then we will excite the patches all at once, and we will shape the beam. That means we want to reduce the side lobe, so we enter some amplitudes at an amplitude taper, and then we define some equations. You will see how it works. And we want to evaluate the phase difference because we have two RX antennas, we have two RX arrays, and we want to evaluate the phase difference between them. Yeah? So this is one important design step, design task for the radar. So let's just start. I just reopen the Empire. And now we use a template. Okay. In the first part, we have used a new project. I will use now the templates. Here we have transmission lines. We don't need a transmission line for this, but we want to use an antenna. And there we have the microstrip antenna. So our target frequency will be 77 gigahertz. And first I want to keep the substrate material. I want to use this material. But I need another height because the antenna is this is much too large for the frequency range. I go to 172 microns. And the resonance frequency should be 77 gigahertz. Yeah. So this is a radar frequency often used. There are options. We will insert a near field recording. We want to insert a far field transformation, and we want to have a parameter called length. So the length here can be varied with a parameter. So I just keep everything else and just click OK. So maybe the first part is to save it. Let's call it File, Save As. Let's go back to the desktop. I create a new folder called Patch. Open and save. So at the first point, I want to modify a little bit the lump port. It is now I know in advance how it should look like, so I just make an adjustment here. I hide the group of patch, so I can select my port. This is my port. I just click on it on the port and can select it. And then I use the Open Edit button for the port. I know that the position, a good position is 987, and here we should have 992. So this is usually a part of an optimization, and this has been done before, but it can also be done later. So now this looks like this. And now I want to do the following. I activate the patch again. So this time I don't want to use an electric boundary condition. So therefore I want to define a ground under the substrate. So I add a new group. I call it ground. And then I want to create a box. I don't use a height at the moment. I just create a box. I want to create it under the substrate. I click on one edge, then on the other edge. And now I just want to have 50 units in the below. I can follow the length with the yellow characters here, the yellow text in the left bottom, and I see that the height is now 50 in minus direction. Oh, this was wrong. Once again, cancel, and then again, one click, second click, and third click. Now it's okay. You see that the values here are as intended. So now we have a ground plane under the substrate. Yeah. Good. Now let's check the simulation setup. I click on this button. And now I go to EM setup and enter a start frequency. This should be 72. And the stop or end frequency is 81 gigahertz. And the target frequency is 77. That's okay. Let's go to the boundary conditions. Here I want to have absorbing boundary condition, but also here at Zmin, because we don't want to use an electric boundary condition at Zmin, and therefore we have included now a ground plane, so that we have also a backside radiation. Yeah? Okay. Now let's save each step. Okay, now let's have a look at the variables. Maybe you remember that we have allowed to have a length as a sweep parameter. And if you go to the slider, you will see how the geometry changes if I move the slider. Yeah? And I expect that we get different resonance frequencies. And I want to find the best length for 77 gigahertz. So I save again, go to Simulation tab. And here we have simulation. And here we have parameter sweep set up. And we have also optimization set up. With optimization, I can define a goal. But this time I just want to have a parameter sweep. I create a new parameter sweep. And this is the configuration. That means that we have a start value and a stop value and a certain step. And now we can start the simulation. I can already start on my computer, on my laptop. This will be quite fast, but I can also enable some more hosts. Yeah? And at IMST, we have different machines available, and I make a distributed computing. That means I can select some of the hosts, and so it will be faster. Yeah? So I have 3 hosts now. This is busy. Let's use another one. Let's use this one. And I will just start now the parameter sweep. So there will be, in total, there will be 11 simulations with the different variables. And we will see the progress of the simulations. You see already there are 2 already completed. And if we have more, now you see that the simulation is quite fast. And these are still running. It's also ready. Okay. Now all 11 simulations had been done. Now I go to the 2D results and I say, you see that there are about 6 or 7 already selected, but I want to say show all. That means I make a right click and say show all. And then we see there is 77 gigahertz is not exactly matched here. It's something between this curve and this curve. So it's here between 1150 and 1150 is 75. And now we can use an optimizer that it automatically gets the best value for the length, or we can just calculate what could be the best one, and I will just use it from my results. Then I go back to the 3D design. I just edit the length, and I use now not stepped but a constant with a value of 1159. This is the one which was what can be found with an optimizer or with a linear approximation, linear interpolation. To verify it, we just simulate it once. Now it's running on the remote machine. And it's finished already. And now this is the new one. And you see it now, it's exactly at 77 gigahertz at matching. By the way, if you like to place some markers, you can add markers here and place it here in this position. You can have it in nice, and you can enter the value here to get this value there. Okay, this was in principle the patch design. Now we have found a good antenna shape. So we have get the desired length. And now I want to create an array. Maybe just as a first step, let's save this result in a new folder called array. So how we can create an array from this? Well, there is a function called array copy we will use later for the patch and the port. But before we do this, we want to, okay, let's go to the 3D design, sorry. For the patch and the port, we make an array copy. But for the substrate and for the ground, we want to oversize it to have a large ground. To do this, I open the group substrate. There are the components, and I can just open the point 1 and point 2. Let's get some new sizes for this. Just double click minus 12,500, minus 7,000. And point 2 should be 8,000 and 4,700. And now we make a zoom extends. Okay, this was the substrate. And now we do the same for the ground. Oh, wrong. Should be a minus sign. Now we have extended the ground and the substrate. The next thing is to make a multiple copy. So we want to create an array, and I want to select the port and the patch. So I can just click on this, but yeah. So this is also the same effect, yeah. So I have selected the both, but I can also use the control key and make enter a window, and I also can then have two selection. You see also the selection is in the lower left. You see the selection are two objects now. And with this, I want to create a copy, a multiple copy. This is the function here, array copy. And I want to make an array, 2 columns and 7 rows. To do this, I click array copy. I want to make a rectangular array. There are also linear array possible. Distance is in X direction minus 2,500 microns. There should be 2 columns. And I want to change the port number. Yeah? Now I have port number 1, and the second column should have the port number 2. So I make a port increment. So I say here 1. And then I go to the rows, minus 2600. Should be 7 numbers. And here I don't need any port increment. I keep the same port number for each for each column. Now I click OK. And now let's have a look what is done. Okay, this could be jetzt now that this can be interpreted as a first column. This means this could be an RX column and a second RX column. So this is a yeah. So there are two RX channels in the moment for the antennas or for the radar. And my aim is to excite once this row, this column, and in another simulation to excite this column, the lower column, and then evaluate the phase difference of both results. Yeah? This is my goal here. Okay, now let's have some more adjustments. I want to check the field monitors. I want to show field monitor 1 and hide field monitor 2. 1 is EM far field and 2 is a complete EM field. So I open the far field monitor with an arrow, and there is a display origin. Currently, it's set in the area of the first patch, but I don't want to display the far field pattern here. I want to place the far field pattern at this. For this, I make a right click here and say pick coordinate. I want to display here in the middle of this patch. The middle is always indicated with a yellow dot. If I cannot access the value, I can zoom in and look for the yellow dot. Here, this is the center. This will be my display center for my far field. Okay, now let's edit the field monitor. You see that it's already defined at 77 gigahertz. I make a processing the far field setup 1, which is the angle phi equals 0. This is the cut in this direction. Here I want to modify my start and stop angle. My start angle should be minus 60 degree, and my end angle should be plus 60 degree. With a resolution of 1 degree. Okay. Now you see that my origin is still here in this area, which is not very fortunate to have the origin in this area. Usually it should be located in the center of the patch of the substrate. I want to change it. Yeah? So for this I check the cursor stay on grid, so it keeps the Z equals 0 position. And now I want to enter a point. A point is entered with I go to the location. Here is my center. And here I make a shift click. Now, then it turns to blue. So I've entered a point now, and now I can change the coordinate, change origin of world coordinate system. And you see now that my origin is now in the center of the substrate. Okay, now let's start with the simulation. Here I have about 14 different ports, and there is a control for the ports, which is located here in the top. And what we see here is the sources editor. We see in the first column the number. We see two different numbers, 1 and 2. And with this convention, all ports with the same number are excited once. So we have our excited at once. And in the first simulation, we only want to excite with a port number of 1. So I disable the port number 2. So that means all ports which have the number 2 are only used for termination. So there is a load with 50 ohm. And all port numbers with port number 1 are excited at once. Also with 50 ohm, but with excitation. Here we can see the amplitudes, load impedance, phase delay, and so on. So we can enter everything. But first we make a simulation with a constant amplitude distribution. So we click on OK. And we see that some ports have an E for excitation, and the other ports don't have an E, just the port number 2. So let's start the simulation. Also here you will see it is quite fast, the simulation. It's only post-processing at the moment. The longest part is the far-field transformation at the end. Especially the 3D pattern takes some time, but now it's finished. Now let's go to the 3D results. Zoom extends. And we see now the pattern of the first column. You see that it's very narrow in this area because we have 7 patches. So it's very narrow because we have here a column in 7 rows in this column. So it's quite narrow. And in the other direction, it's quite broad because only 1 patch. So this is the radiation of 1 patch. But especially in this direction here, you see there are quite high side lobes. Using this you see that the side lobes have an amplitude of about 3 dBi, and this is not good for a radar because it would have ghosts in your view. So our next task is to remove the side lobes, and this can be done by shaping the amplitudes. So currently they have all the amplitudes of 1. So the amplitude is of 1. So we want to have some kind of a taper for the amplitudes. And this can be done in the following. I switch to another view table style. I go to the array view. And I switch to the parameter of amplitude. You see now the amplitude is 1. And now I can override the amplitudes if I want to, or I can use a calculator and enter an expression. I already have this expression available in my because I have used it already. And you can enter some formulas depending on the index. Here I use the index. That means my index in y in y direction, or I can use index in x direction, or I can use x in position in units, or the number of columns, and so on. So the easiest thing would be to have and this gives us a Gaussian distribution. Yeah, so that means if iy is 3, then this is 0, and this expression is 1. If it's different from 3, it's symmetric about 3. Yeah, so the port number 3 is the center, and if I go to, let's say, port number 2, or so on, then this value is lower. I just apply it, and then you see the result. You see that the port position 3 has now the amplitude of 1, and we have here a decaying amplitude to the side. Yeah? So at the side we have only 1/2. In the center we have the amplitude 1, and again at the other side we have again the amplitude of 0.5. And this is also done now for both of these both of these antennas. Okay, let's just look for the difference. Let's have the new simulation. That's also the advantage that is very fast. Now waiting for the post-processing. And let's go back to the 3D results. And now you see that the side lobes are very small now. It's in the range of -10 dBi. Before it was here in the range of 3 dBi. But now it's we have only one main lobe practically. And this is what we want to do in our radar application. Okay, now we have calculated the first port. Now let's go back to the tab and select the other port. Therefore, we go back to the detail view. Now we switch all off and only use the second port. And do a simulation. Again. Post-processing takes longer than the simulation itself. Now let's go back to our folder. Just to want to show, we are currently on the desktop and in the array. This is the project folder. This is the one we are currently simulating. And here we have the folder. And you see here, there are now two subfolders because we have in principle two simulations, two ports which were excited, and each subfolder contains all the results. For example, here we have the directivity, different cuts, different components. Every one has also a log file where we see, for example, the lobes and so on. And these files will be used now here in sub 1. This was for the simulation of the first column. And here, this is the results for the second column. We can see it also in the 2D results. This is the S parameter. I use another plot type called far fields. These are the far field in rectangular. I only want to show now the results with phi equals 0. You see here are the results for phi equals 0. These are the results for phi equal 90. Yeah, this is the small side or the narrow side, and this is the broad side. And I want to show, so I could everything which is for the phi equals 0. I can select here and sort it, and I select only the theta curves. And then we can say show only an auto color, and let's zoom to make an auto scale. And we see now this is the angle range from -60 to +60. And this one is the far field for the column number 1. And this one is the far field of column number 2. And now my aim is to have the phase difference of these two curves. Yeah? So when I go to the not in the log magnitude, I could go to angle, but you see now it's hard to determine the phase difference between the two curves. Yeah? Or let's go back to phi equals 0. E theta, show only. Yeah. So it's hard to determine the phase difference here between. And I want to use equations now to calculate the phase difference. So I have two result curves, and I want to make some further post-processing to get the difference of these results. For this, I go to the Simulation tab and click on Simulation Setup. Here, I have a section called Equations. And I can add some equations in different folders. Typically, in this case, I have my folder number 2, and I want to add an equation here. So I add an equation. This can be a symbolic equation, a calculation, or a file copy. I make a symbolic equation. I call this a new file, farfield 1, ff1. And here I I add a source. So the result will be FF1, and the source will be now coming from here. Sorry, I have to check. Yeah, I need the complete name. Yeah, so I go to the folder and I have to enter the name. That's the phi equals 0 and the e theta. This one. I just copy the complete expression. And override it. So the first position. Okay. Now I have to, this is the file name, and I have to assign a location. It goes back one folder back and comes from the subfolder -1. Make it larger. You see it now that I use the far field results from folder 1 with a phi equals 0 and the e theta component. This is sorry, I made a mistake. I make a file copy. Sorry, this was for this. Destination FF1, and my copy should be from subfolder 1. I have to use the theta component. But I have to add this one. Okay, this is the first copy I would like to make. Now I just copy to clipboard and paste from clipboard and edit. I make the same file from the subfolder 2. Oh, the destination should be another name. Destination FF2. Okay, this is not an equation, but this is just the file copy. That now I have the file copy available in a new folder name, which is with a new name. So I just have in principle, I have made a copy from one folder to another folder. Okay. Now I enter a symbolic equation. Now I want to create the ratio of this, and this means I call it FF ratio. Then the first source is FF1, this which we have created here. The second source is FF2, this is this one. And I want to create the ratio FF1 over FF2. And I can set a label, phase difference, for example. And now I have created a symbolic equation for this. Maybe another thing is to have a theory curve at another equation. Let's call it FF theory. As source, I use FF1. it will only be used for the x-axis. Yeah? So I don't use it in the term. It will only be used for the x-axis. Let's call the term. It's one for which you are seen in the radar presentation, which is in principle following. We had J times 2 times pi times the frequency 77E9 times the distance of the columns. This was 2.5 E minus 3 times sinus x dot pi over 180 over the light speed of light, which is 3E8. Yeah? So it's just a formula for the theory curve. I hope I did everything right. J2 pi 77E9 2.5 E3 sinus x times pi over 180. I missed a bracket at the end. And now I can compare the phase difference of the simulation with the phase difference in theory. Okay, click OK. And now I only make a new post-processing. No, not a new simulation, but it's just a new post-processing. And I look for the log window. Of course, it makes a new far field transformation. I could have switched off the far field transformation if I want to save time, but I think it's fast enough. Okay. Now you see in the last rows, the post-processing says my file copy, two ones, FF1, FF2. Then I have the first equation. The phase difference is the ratio of these ones, FF1 over FF2, and the theory curve is this formula we have seen in the radar theory for the phase difference. Now let's go to the 2D result tabs, and we see here these are the far fields. Let's use another tab, another result, and we use not the scattering parameters, but the custom curve. The custom curve is the one when we define an equation. And here you see the FF ratio in real and imaginary part. And I want to see the angle in degree. And this looks like this. And if I want to, I can add a file in the subfolder 1, a subfolder 2, which was called theory, which does not has a label here, and therefore is not listed. But this is the theory curve. Yeah? So did I do everything right? Let's go back to yeah. You see that it's the theory curve, the blue one here with an agenda. The blue one is the theory curve. Is quite close to the green one, which is the simulation, but not. Yeah, it has some deviations. Yeah, so you see that this is not an optimum design. Yeah, so maybe you need to have more design aspects to make it more linear, for example. But this is a design task. This can be, of course, you need some experience for this, but in principle, this can be done quite good with the software, especially when it's very, very fast. Huh? Okay, this was the tutorial for the radar. I'm looking for some questions. Okay, I just open it again. So I will show how to get the axial ratio and also other types of polarization. But front to back ratio is not easily obtained. Yeah, so our front to back ratio is, let's go back to the results. Okay. So here for the, oh sorry, wrong one. To the far field monitor, and here we have the far field settings. So by default, the components are the magnitude, the phi polarization, and the theta polarization. In some cases, you have a circular polarization, then you can select LHCP and HCP, and also the axial ratio. Yeah, so this, then you can select these curves. And another thing is that you can have Ludwig III co and cross polarizations and determine the polarization angle. But the back to front to back ratio, it's not a value which is automatically obtained. Yeah, so sorry for this, but if I go to the results, I'm not sure how to get the front to back ratio, because we have here quite high simulations. Maybe you could just have a look at the pattern. Go back to the pattern. By the way, you can also look at the far fields in this mode. Yeah, so you have here the theta angle and here the phi angle. So let's, if this is the front and this is the back radiation, then this is the ratio. Let's say from this value to this value, or you can go to the far fields, the metadata. You can get the angle of maximum value. You can get the maximum value in dB, total efficiency, radiated power. So maybe you need to read this from this value. If this is the back radiation here, this is the front. This is about let's do it in this way. I'm a 0 and 180. So then the ratio is 15.5 minus, and here we have -6. So it's about 21, 22 dB. So this is, I would say, this is the ratio between front to back radiation. Good. So you don't need a remote system as I did, because I just wanted to make it very fast. It is not required. It can also compute on this local machine. Yeah. So this is not a. I have here a laptop, It's a Core i7, and it also simulates the structure quite fast. So it's not needed to have a remote system. Yeah? The remote system is just for convenience, I would say. Can we get mixed mode as parameters from single-ended? I'm not sure about this. I think maybe we should discuss this single-ended. So maybe you mean differential or common mode. So when we simulate a microstrip, we have always a common mode. No, the common mode is used if you use a coplanar waveguide. Yeah? So in principle, we have always a single mode, which is then differential between ground and signal. Okay. The maximum gain. Yes, you can get the maximum gain. It's written in the meta file, in the metadata, and here you see the maximum value. So first I have to say that the simulation I did until now was for directivity. But if I want to have the gain, I have to use another normalization. Currently it's directivity, but you can change to gain, the real gain, or the maximum value. But if you change to gain, then you get the gain value, of course. And then in the result file, you get in the metadata, you get the maximum value. Maximum value. Not sure how to see it. We are in the results here. Everything is out. Let's go to the 90 degrees. It's only 1 point, of course, it's 15.5 something. So this is the maximum value in the file. Maybe I just show you this one. Of course, the maximum value is also written here. Yeah, so the maximum value is here 16.1 dBi, and in the log file, you can also see the maximum value. Here I go to the 3D log file, make the magnitude. You see, for example, the maximum here is 15.5. This is not the right one. Okay, but you see also the theta value and the phi value for the maximum. Good, but you see it's only a single frequency, yeah? And the thing is, you can enter, of course, in the far field setting in the monitor. Here you can enter frequencies, yeah? So you can, let's say, you can have 100 frequencies with 100 megahertz step, for example, or with the 10 megahertz steps, or let's say, let's say 100. Start value should be, let's say, 72, and this is a stop. Then then you have 100 frequencies, but this takes longer simulation, of course, and it takes more memory. Yeah, so you need to store the complete frequencies, and what's even worse, the simulation is not the problem. The simulation takes not much longer than that, but it takes more memory. Yeah, and especially the post-processing takes a long time. So I would not recommend this to use many frequencies. No, it's not possible to get a lump model of our antenna design. No. It's all 3D, and we only get the S parameters. Yes, we can also use a wave port. A wave port is very similar to the QTEM port. Yeah, so we call it QTEM port, which is is also used for coaxial feeding, but we have also a coaxial port available. Yeah, so we can use both. Sometimes it's better to use a coaxial feeding because it's shielded. Yeah. So, but we have very similar as a wave port in other software. Okay, how to set up ports? I think I have defined it. So we have here lumped ports under the patches, and here we can set the amplitude and the phases for the ports. Okay, here maybe I have some troubles with the software. Maybe you can write a soft. Yeah. Okay, we have already discussed it that when you cannot get the bottom, you need a certain resolution of your window. Yeah, so otherwise it does not work. Okay, so let's go back to the top. Okay, we have everything. Maybe just a very short to show you the integration of this antenna into a real environment. But I will not do a tutorial from this, but just to show you a little bit what is then how this can look like. Usually it starts faster, but maybe because of the presentation, it takes a little time. So this is the array as we have seen, as we have designed. But here I have already integrated a car model. I just switch on the different parts. And zoom extends. And go to this view. So here we see that it's very slow. The antenna is integrated behind the bumper. And you see when the bumper is the back side of the bumper. This is the bumper. And the antenna is closely behind it. And I already did the simulation because it takes little time. And just go to the results. Again, we have the car model, the antenna. And let's have a look at the field monitor. Maybe first the far field. Let's go to another view. Oops, Sorry. You see that there are side lobes again due to the bumper. I think so. Maybe I go back to 3D design and go back to the port setup. Yeah, you see that the shape, the amplitude is shaped. So it should be with less side lobes. So the side lobes are in the range of 0 dB. Yeah, so, and also the broad pattern is a little bit changed than before. Yeah, so also the integration of the bumper is something which has to be considered in the design. Yeah. And also it depends on the material of the bumper, of the painting of the bumper. So there are a lot of things which have to be considered in the simulation. Maybe we go look at the near field, and you see also the near field here that the bumper has some effects here. You see there's a shadow region, and there is some kind of a wave trap inside the bumper. And if you go to the animation, we see it here. By the way, if you want to save the animation, you can export it here as an animated GIF. Yeah? And then you can use it in your PowerPoint, or you can for a presentation, or you can do it like this. This is done here. There are two formats, which is called UGV file, and we have also animated GIF. I think OGV files are I think have a better quality. You see there's a render and export frame of 24 images. The number of images means how many phases we are using for display. Now the render is finished, and I can switch it off. And if I'm right, this should be then in the array. It's on the desktop. There's the OGV. Oh, I forgot how it works. Okay, but I'm not sure where it was saved. This is step 33. Step 33. Then it's here in this now. Tutorials, step 3. Here it's located. I think it can be. I'm not sure which can be done with this. Or I use a special player for this. Oh, I don't have the right app here. I think it's VLC. I think it's called VLC viewer who can use this format. But anyway, you can also export it as animated GIF. But the quality is not as good as the OGV file. It's still running. It's finished. try this one. Yeah, now it's running using the standard viewer of this. Okay, I hope I could show a little bit of the software. But let's look for some. The record session should be available within this team. So with the recording can only be viewed in the team session. But if we can also, I can also send the presentation in PDF format. But I think the recording should be working. Let's look for some other. Okay. Diversity for the array antenna. I'm not sure about what. Some details about SAR. Okay, this I can show. SAR means usually that you have recorded the field inside a human body. Yeah. So, for example, I load a new project. In the examples, you will find SAR, and maybe just use the monkey thing. So this is a small monkey model, and here we see that the SAR distribution. Yeah. So in principle, the workflow is as follows. You record the field in a volume which is enclosing the model, and then you can have in the plot options of your field monitor, you can select different field values. So if you have a volume recorded, you cannot get only the electric and magnetic field, but you can also get the current density, power flow, the spatial average power density. This is a new standard for high frequency. Or here you can set the specific absorption rate. Yeah? Then it's also interesting for low frequency, it's internal average E field, and also the average current density is something which is quite often used. But here we use the specific absorption rate, and we can specify an averaging mass. It can be 10 gram or 1 gram. And so we can just calculate the SAR values now. And yeah, this can be done in different planes, of course, and but it's a part of a post-processing. Yeah? So you will find some examples also for SAR in this software. So I don't know this publication, and I don't know the Doppler simulation. Maybe you can. So I don't know details about this. Maybe you can send an email to the contact, and I can forward it to the radar specialist. Maybe this would be the best option. Okay, thank you very much for your attention. I hope you have seen a little bit inside of the Empire software. Please try the software. You can download it. You can get a free license for trying and testing the software. And I hope that we can have can be a good alternative to other software tools. And I hope you enjoy it. And I also hope you have enjoyed this session. And thank you very much for your attention. And yes, please ask questions on also afterwards using my contact detail. If you want to have more downloads or the presentation downloads, please let me know so I can share it with you or give it or create also a download link for this so you can have also the presentations. Okay, thank you very much, and we are just in time, and thank you very much and have a good day and night. Thank you and goodbye.